Good morning, everybody. I'm going to get started with the presentation in just a few minutes. My name is Steve Smith. I'm one of the organizers of the StirTrike conference. Can I see a quick show of hands for those of you that are in my theater? How many of you, is this your first time at StirTrike? A lot of you. Nice. All right. How did you know to get your tickets super fast before all the veterans snatched them up? That's good on you for getting those tickets. How do you like the venue? Everything good so far? All right, we have a question channel here for this theater, and for this session in particular. If you have a question, I'm going to have a lot of content to cover. I'm going to go really fast. And so if you want to ask me anything, you can ask in that Slack channel. If there's time at the end, we're going to check that and answer here. And if we don't answer here, we'll answer in the Slack channel. You can also find me online. All my information is up here, so you're welcome to email me, steve@ardallas.com, or online, I'm at @ardallas. Turns out, funny story, if your name is Steve Smith, it's really hard to get any variation of that at a URL or a Twitter alias or whatever. So everywhere online, you'll find me as @ardallas. Let's see, anything else? Any feedback on the conference to share? Good, bad, or otherwise? We still got a couple minutes before we get started, like one. Wi-Fi, yeah, it turns out, funny story, movie theaters don't like having lots of connectivity and Wi-Fi set up. So for some reason, I don't know what it is, but they don't have that infrastructure, and they really don't seem to want it either. And so that's one of the downsides. You have really comfy seats and no Wi-Fi. But that means you might have to focus more on the content while you're here today. Otherwise, just make sure you brought your extra battery for your phone and that you've got a good data plan for one day. Anything else? We know about the Wi-Fi issue. It's just not something we can do anything about. Spread out the breakfast. We did that last year, and we did that with lunch last year too. And a lot of people didn't find the food that was in the back halls and other areas. We could probably spread it out more in that main open area, though. I'll go with you on that. Looking at how things were, and the other thing I would have liked at breakfast was to have like more tables to sit at to actually be able to eat your food. But we're limited in space, and there's 2,200 of you, so there's only so much we can do with the venue. But overall, we're really happy with this venue. All right, so it is now exactly time to start, and I don't want to waste any of my time that I have for this presentation. So in this theater and in the overflow theaters that this is streaming to, hopefully successfully, we're going to be talking about design patterns and cloud architecture specifically. So I've done a lot of different talks on design patterns for object-oriented programming. These are more like higher-level patterns for architecture. Another couple resources, if you like, before I get started. I have a podcast. If you're interested in developer tips, you can find there. I have a mentoring program at DevBetter, and then there's a free Microsoft ebook, if you haven't seen it, that you can download. I've got a link to it from my website, but you can also just Google for eShop on web to get that. So if you want to snap a quick picture or anything of that, or otherwise all the slides and presentations will be recorded. You'll also find all the slide decks, at least for the speakers that give them to us, will be on GitHub. If you go to github.com/StirTrek, you'll find this year's conference should have all the speaker decks after the show. And if a session you're looking for isn't there, just harass that speaker to put it on GitHub. All right, so before we get started on talking about the cloud, I want to kind of set the stage on like, why are people moving to the cloud? What's the reasoning behind it? What problems is it solving? And so I want to take a quick trip back to where kind of the web programming started. And this will date me a little bit because my career pretty much as a professional software developer pretty much coincided with when web development really started to get big. So we're going to go back, but not that far. And we're going to look at, let's say, 20 years ago is a good round number, to a simpler time, when this is what a web server might have looked like. This is a compact alpha server from 1999. It's this huge box that wasn't rack mounted. Had a whole bunch of hard drives that you could shove in it. Lots of moving parts. Everything was spinning. It had fans, just like our servers have today, but it also had every single disk drive in there was spinning somehow. So things failed a lot more often than today when we have solid-state drives and almost no moving parts in a lot of our servers. I have one of these weird things that you could use. This is actually a save icon receptacle. And so you can take save icons and put them into this thing and pull them out. And so that's how you would save things with these servers. You could actually use that to install stuff. You would use the A prompt. How many of you have ever used an A prompt on your machine? Oh, most of you, awesome. Is there a reason to use it other than floppies that I'm not familiar with? No? Okay, just a lot of you have used floppies. Awesome. Cool, my people. All right, so you'd have to use the A drive to access the 3.5-inch floppy drive, and you could install, I don't know if you can read this from back there, but this is Windows NT Server came on just 3 floppy drives that you could install to then run classic ASP if you wanted on this 90s era server. All right, so a typical early way of hosting a web application was to have one web server that did all the things. And so it would look kind of like this. You'd have a client machine, and it would talk to the server. Now, today, more than half of the traffic on the internet is mobile traffic, right? People coming in from smartphones. But in the 90s, of course, people didn't have smartphones. So this client machine is not a phone. It's probably an actual desktop PC. It might look, I'll show it in just a second. But the server architecture has basically the app and the database potentially on the same machine, right? Machines were expensive. You didn't always start out with having a separate database server, and so this is the simplest, quickest architecture that you could have, is just everything's on the one box. All right? You also would have what's called a webmaster. That term is still around, but I don't think it's nearly as popular as it was in the 90s, but everybody was a webmaster of their website back then, which was the original full-stack developer, because they did all the things. Most of the stack was on the server for the most part, because HTML5 wasn't out and all the JavaScript frameworks weren't available. Okay, so your computer that's hitting this, it's probably an actual desktop PC. It might look like this. This is a desktop PC from the 90s made by Packard Bell. I actually owned one of these. They weren't very good. They're no longer with us, which is probably for the best. You would take this computer, and it had no native way to talk to the internet. And so you would find one of these things laying on the ground because AOL had carpet bombed the country with them. And you would just go out in your front yard, and you would pick one up, and you would throw it in your computer. All right, and you would install this, and there would be an icon then on your desktop that you would click on. And it would let you connect to your modem that you had to make sure you bought a computer that had one of those. And then it would connect to a phone. So you're still connecting over a phone. It's still kind of a mobile access to the web server because it's using a phone, but it's not a wireless phone, right? And now this is a rotary phone. How many of you have ever actually made a call with a rotary phone? All right, you guys are my age. Okay, awesome. The rotary phone, fun fact, was actually the inspiration for, if you squint your eyes a little bit, the original iPod, rotary navigation menu, okay? So the rotary phone was great because if someone had a phone number, had a lot of 9s in it, it would take twice as long to call them as if they had like 2s and 3s in their number, because you had to wait for the thing to reset after every call. Now, you didn't have to use a rotary phone for your modem. You could use whatever connection, but you would ultimately tell AOL on your client, on your PC, to go talk to AOL in the cloud, and it would sound something like this. So once all of that happened, right, you would finally be able to talk to the internet at a blazing 14,000 bits per second or 28.8 or ultimately the super fast one was 56.6. And you would get to this server that we already talked about. And now you could make HTTP requests more or less like we do today, like earlier version of HTTP. The server would basically run everything on the server. It would run stuff in languages like Perl or VBScript or things like that, maybe Java a little bit at the end of the 90s. It would do its work. Probably it didn't have any notion of separation of concerns or anything like that, so it would be run some script, go get some data, start showing HTML, grab some more data, show some more HTML, and eventually you'd load a page. And the page would load like this, very slowly, right? Because it's coming over the modem and also because the server is slow. Everything was slower back then. And so this actually is one of Amazon's early pages. So they've come a long way. This was Amazon.com, version 1, and they had 1 million titles and a really cool logo that I think is supposed to be a river. So they've moved on from that. But this was web programming in the 90s. Okay, so let's talk about how we could assess this architecture in terms of sort of a report card based on these different characteristics represented by these icons. Now, before I get into this, I haven't told you what those icons are. So let's take a step back and talk about what are the different considerations and challenges for web apps in general, and specifically for cloud-hosted web applications. Once you decide that you're going to host your app in someone else's data center instead of you owning all those servers and managing those servers yourself. Okay, so the first one with this icon here of what I think of as uptime is called availability. And availability literally means like how often is your system or service up. Whenever it goes down, the clock is ticking against your uptime number that you want. And it's usually expressed as a percentage. So many of you have heard of like trying to get 5 nines or something of uptime. If you have 99.99% uptime, or if you're trying to get that, that means you're on average you have 1 minute of downtime per week. And so if you're having more than that, you obviously have less than 99.99% uptime, and so that can be very expensive to achieve numbers much higher than this if you have any kind of downtime for maintenance or unplanned outages or things like that. All right, so we're going to evaluate these different scenarios, architectures, patterns based on the impact they're going to have on our system's availability as one of those considerations. The next one is data management. Data management basically has to do with where you're keeping the data that the application needs. And in a cloud-based environment, there's usually a lot more options for this. And because you don't have just one database with everything in one place, you have to worry about distributed data. You have to think about how to keep it consistent and how to synchronize things between applications or different parts of applications. Then we have design and implementation. One of the key things here is going to be consistency, because as you take an application and you start to move it across multiple machines or multiple different services or things in the cloud, you want to make sure that the way all of those are set up is consistent. You want to look at factors that will determine whether or not you consider your design to be good, will be based on whether or not it's easy to maintain, how easy is it to administer, how easy is it to develop for is always important. You want to be able to have access to good diagnostics, so when things don't work, you're able to quickly determine what the issue is. And then, of course, cost. Depending on what kind of design you choose, unlike traditional, you own all the servers and they're in your basement of your office building, cost will vary dramatically based on design decisions you might make for just like how you want to lay out the different pieces of your application in the cloud, whether that's Amazon or Azure or whatever it might be. Okay. The next consideration is messaging. Messaging in this case, even though it shows a couple things that look like email icons, we're not necessarily talking about sending email so much as how are the different systems going to communicate in the cloud. And so, in a traditional architecture like the one we just saw, where there's literally one web server with one database, you don't really have to worry about messaging, right? Everything talks to the same thing. It's all in process, or at least it's all on that machine, and everything's in one database, so it's all in one place. It's easy to keep everything consistent. When you have lots of different subsystems that make up your overall application, or many applications in your enterprise or your org, you need some way for those to communicate back and forth. And it turns out that just having one database to rule them all is not always the best design. And so coming up with ways to do messaging either through direct synchronous calls or some kind of asynchronous messaging, a message bus or message queues, turns out to be very important. And there's trade-offs for each of these. Okay, so then next you want to talk about what are the management and monitoring options here. So you can't necessarily, in a cloud environment, just remote desktop in as administrator and do whatever the heck you want on the server. And so you need to have other resources available, because typically with the cloud, if you're not just using VMs, virtual machines, you're going to need to access what are called platform as a service, or PaaS resources. And the tools you'll use for those will be some kind of online portal or some command line tools that you'll have that'll let you manage that stuff. You want to treat your cloud resources more like cattle or herds of cattle than like pets. Right? Your pet, you're going to give it a name, and you're going to care for it, and you're going to have some emotional attachment to it. And that's how you think about your servers that are sitting in your rack if you're an IT administrator. Whereas in the cloud, you have no idea what hardware that's running on. You just have different apps or different containers or things like that. They don't have a name. They don't have any emotional attachment. They get spun up and killed off anytime you need them to in response to the demands for your system. Okay, so then the next consideration is performance and scalability. These two things are often grouped together. Anytime you hear about it, everybody will talk about performance and scalability as like one word. But it turns out that they're kind of opposed to one another, and they mean different things. So performance simply means how responsive is the system to a request. So if you have a web application and a user comes and hits your home page and it comes back in half a second, then that is a measure of its performance, right? How quickly it was able to respond. That doesn't tell you anything about how scalable it is. If that web server is running on like really poor hardware, and the way that it does that sub-second response time is by maxing out its CPU just to do that, as soon as you have 2 users hitting it, maybe each one now takes 2 seconds for the page to load. That's not very scalable, right? Even though for one user it was very performant, or at least probably performant enough. So how the responsiveness changes as load increases is how you measure scalability. So even if you have a really poor performing site, like every single page takes 10 seconds to load, but it does that whether there's 1 user or 10 million users, it's very scalable, right? It doesn't change with the load. So when we talk about scalability, there's going to be 2 options typically that you're going to look at. One is scaling up. So when we talk about scaling up, we're talking about taking your server resources and adding additional resources to them, right? So on a given server, you could increase the CPU. If it's a virtual machine, you could give it more cores or more CPUs. You could add RAM. You could give it faster hard drive or faster network access. Any of those things will scale up that individual resource's capability. The thing about scaling up is it always has a fairly finite number of steps that you can take it before it's maxed out, right? We don't typically provision servers that are like the very bare bones minimum of what they can support. And so with possibly the exception of memory, there's not usually that much further that you can take them up to increase the speed. A lot of servers today can take terabytes of memory, but most people aren't using that. So the other option then is scaling out, and scaling out is simply adding more instances of those servers. All right, so, and that you can tend to do a lot further than scaling up. Then we have resiliency. Resiliency just talks about how easily the system can recover when bad things happen, preferably automatically so that you don't have to be involved. You don't have to wear a pager, or if you do, it doesn't go off at 3 o'clock in the morning on Saturday. And so you want the system to be resilient to failures. And then security. Security is more important today than it's been in a long time. It's actually a very huge growth industry of security professionals. You want to make sure your application is protected from attacks, that all of your data is protected both on your system and in transit to your users, and that you restrict access to approved users. So users can't see things that they shouldn't when they access your system. All right, so now we come back to this simple architecture where you have a single server, it's got your app running, it's got the database or whatever data it needs, might even just be files. It's all running on one box. How does it match up on here? What kind of grade would we give it? So for uptime, it's kind of meh, right? Like anytime you need to deploy this thing, it's going to take the site down probably. Anytime it needs a server update that needs a reboot, which they all did back in the day, it's going to have to be down. So getting that 5 nines of availability is going to be really tough with this design. Your data architecture, your data design is easy, right? Database is all in one place. There's only one thing. It's easy to keep consistent. Likewise, the design considerations, it's about as cheap as you're going to get for this design. Everything's in one place. It's simple to develop. It's relatively simple to maintain. You don't need any messaging, so that's easy. Monitoring is also easy. It's just one server. Your performance is great, but also not good because it's performs reasonably well, especially because the database is on the same box. So there's no latency between the web server and the database server. All of that's going to be super fast, but it's not going to scale very well. Once you start to max out that machine, because of the database or because of the web server, either one, it's going to start to slow down. With resiliency, that's this sort of like neutral. Same thing for security, right? Depending on how you implement it, it could be good, it could be bad. They aren't really impacted by this approach. Okay, so you've delivered this solution. It's kind of the simplest possible thing you could do. Most organizations skip this step because they already have a database server somewhere. They probably have a dedicated DBA, and so they're mostly going to do the next one, which once you have more demand, you move to anyway. And so the reason why you would do this, if you didn't already have a separate database server, is you're going to start to max out your vertical scalability. That server can only do so much, or maybe you don't have budget to get more resources for that server. It's cheaper to just buy another server for the database. And so your performance at peak load times is starting to suffer. So the remedy here is take the database off the web server. And so now you've got your web server and your database server separate. One thing I didn't mention on security that I forgot is the one downside to that approach of having everything in one place is if somebody owns your web server, they also have access to your database server, right? Whereas now, once we've separated them, we can make it so our database server is more protected from attacks that might just take down or gain access to the web server. All right, so now this is pretty standard architecture, right? You've got a web server with a separate database server. Most of the considerations are now still the same. Security is a little bit better. But it's not unusual to have some parts of the application that are slow. Like you have an application that most everything works just fine, but there are a few queries that are made or a few reports that are run that take longer than users would like. And maybe when those run, it causes so much resource load on the database server that it impacts other users sometimes that weren't even doing anything that was that contentious. And so when you assess this, if you've maxed out the vertical scaling capability of the web server and the database server in this case, or you've maxed out your budget, which is the same thing, now you've got to come up with another way to improve performance and continue to let the system respond to demand without just trying to scale up. The cheapest approach usually is scaling up. There's a saying that I heard early in my career, which is called hardware hides many sins. So you can write really crappy code that doesn't perform very well, and as long as you've got enough hardware behind it, nobody will ever know, right? And so that's one approach, is just throw more hardware at it. And it's usually cheaper than hiring a developer to go spend a week trying to optimize queries and make everything cleaner from a performance perspective. All right, so now let's assume that we've already done the database tuning that we can do. We've added the indexes, and we've done all the stuff that we need to make sure the database is as fast as it can be, the hardware is as much as we can get, but still some queries they're just expensive queries. There's nothing we can do about it. We've got a lot of data, and it's slowing things down. So the first pattern that we can apply to this one is a pretty simple one. Many of you probably already use it. It's called the cache aside pattern. And there's two parts to this. The first one is this read-through strategy, which basically means that your application, represented by this gear here at the top, is going to first go out and check the cache, whatever that cache is, and there's different technologies you can use for that, we'll talk about in a moment, and see, do I already have this thing I'm looking for in the cache? And if I do, great, just return it, right? And that's going to be super fast, and your performance is going to be much improved. It's actually one of the best performing optimizations you can do is just add some caching to your application. I've seen like 10x improvements in performance by literally just adding a 1-second microcache to a web server so that it didn't have to hit the database on every single request, right? Now it would go from, if the web server is getting hit, this page is getting hit 10 times a second, and now it goes from that down to 1 time per second. The database load drops by a factor of 10, and every page request is faster. So even just 1-second duration caches can make a big difference. If you don't find the thing in the cache, then you go back to your data store, wherever that is, get the real data, and then on your way back out, giving that to the user, you're going to store a copy of that in the cache for next time. Okay, and then the write-through strategy is basically the opposite. When updates occur, you want to make sure that you are wiping out the cache. Now, this part's often neglected, and if you just use a really short duration cache, like if you have a 1-second cache, you don't necessarily have to do this part, because after a second, you're going to invalidate the cache entry anyway. But if you have a cache that does not have a short time frame, or maybe you don't use any time frame at all, you just let it be a least recently used strategy, and your cache, when it fills up, it'll just evict things that no one's asked for in a while. You would like to have a way to get rid of stale data. And so that's what this write-through strategy will do. Now, some caching products do this out of the box, do both of these out of the box. If you're not using one of those, then you have to implement this yourself in code. So when an update occurs to the data store, you take some new value, you throw it in the data store, you then have to go find its corresponding entry in the cache and throw it away, or update it with that new value. Which one you choose depends on your performance characteristics and how much extra RAM you have. If you don't expect anyone to come looking for that data anytime soon, you can just blow away its cache entry. Next time somebody wants it, they'll come through this approach and they'll repopulate it. If you know someone's going to ask for this like really soon, sometimes immediately, like literally in the same request, you're going to do an update, and then like later on in that same request, somebody's going to ask for it, and they're going to go to the database to look for it, then you can put it in the cache so it's there. All right, so there's different types of caches. The easiest, simplest one, and most performant is to add in-memory caching. So in-memory caching lives with your application on the web server. It's super fast to access because it's literally right there in RAM. And so it's going to be orders of magnitude quicker to get to data in the cache than it is to go to the database server to get it. And so this is like the upgraded version of the system that we've got. And so we can talk about some pros and cons of it. There are, unfortunately, there's these two hard things of computer science that we're going to run into, though. The first one is cache invalidation, right? Figuring out how we're going to invalidate the cache. One way to just avoid that problem is to have really short duration cache. The second thing is naming things, which you probably are all familiar with. That's tough. And then, of course, there's off-by-one errors is the second thing that's hard in computer science. All right. Now, this approach has some new problems. Okay, so our performance now is usually better. All right, anything that's a read mostly entry off of our system, which is generally most of the data you need is stuff that you're reading from the database, is going to be much faster because it's going to hit the cache. Now, some users will still complain of delays when they do those expensive queries and they're not already in the cache. They're still going to have to wait for those. There's some strategies we can use to apply to that, but we'll get to that in a minute. So now we have some data consistency problems now, right? We don't have multiple databases, but we do have 2 copies of the data. We've got the actual canonical data store in our database, and we've got a copy of the data now in the cache. And so keeping the cache up to date is a new challenge. If we're not keeping a super short duration, we've got to have some way to do that right through strategy to make sure that we're always blowing away that cache entry. Now, if some other system in our organization goes and updates that database and doesn't go through our application, then it's probably not going to update the cache in our application. And so we'll still have that problem where we've got stale data in the cache. It's out of sync with the data that's now been updated in the database. That means customers may see stale data. They never had that problem before. Before, they might have to wait a while to get the data, but it was always the current data, right? So we've introduced new problems with this solution. We might want to have some new monitoring and some new tools for that cache. A lot of times this gets skipped, but it can be very useful to have a way to clear out the cache or to view what's in your cache on your web applications. If you don't have that, if you're doing typical ASP.NET application, what's the easiest way to clear the cache in ASP.NET? Cycle the app pull, yeah. Or remote into the server, touch web config, hit save, right? Like that, it works. Right? It takes down the whole application, and ASP.NET's not always the fastest at starting back up again. It'll take 2 or 3 seconds minimum, usually, for a web forms app to come back up, but its cache will be clear, right? So that's one way to do it. Now, you could create a tool that will do that and do it more granularly, and if you have an application that you want to stay up a lot of the time, then it would be a good idea for you to do that. But you need to do that now. So I'm giving that a frowny face because you didn't have to do that before. All right, so that is a lot of frowny faces on this page, but don't worry, it's cool. All right, everything's perfectly fine here. It's all fine. Thank you. How are you? All right. So now demand keeps growing. We need to change how this is working out. So at this point, we're going to scale things out. Right? I've mentioned that we've maxed out scaling up these servers or our budget for it. And so we can add more cheap servers better or more efficiently, more economically cheaply than trying to continue to scale up those couple of boxes that we have. And so now we're going to go buy a load balancer. We're going to put that in front of our web servers. We're going to have 2 web servers. It's going to be our very simple web farm. They're each going to be exact copies of the other because we want consistency. They're each going to have an in-memory cache because that's what they have, and they're copies of each other. And so requests are going to come in, and a request might go this way or it might go that way, right? Depending on what the load balancer is feeling like. And so now this has some new challenges and advantages for us. We can scale this out beyond just 2 if we want. We can keep adding additional nodes. And this new behavior gives us even better performance and scalability, right? If we need more scalability, we just buy more servers and put them out there. As long as the bottleneck is the web server, we're going to be in good shape. Until the bottleneck becomes the database server, then that scaling out web servers helps. Still not helping with those users that are hitting those expensive queries, though. Now we have multiple caches that we have to keep up to date. So you might have a request come in, hit the first server, it goes to the database, gets the new value, puts it in its cache, and then returns a response. The very next request, which could even be on the same page load, right? If you've got a bunch of JavaScript running and populating different parts of the page, could come in, hit the other server, which doesn't know about the cache being updated because it didn't do the update, it didn't do the write-through strategy, and so its cache is out of sync, right? And so now you've got to keep multiple in-memory caches on multiple servers in sync, which requires also having all these servers will eventually mean you need more monitoring tools, and you've got more overhead of patching and managing servers. But on the plus side, we can actually pull a server out of the rotation, do any kind of updates we need to it, and then put it back in. We could warm it up and make sure it's primed before we put it back in the load balancer, so users never have to wait for that server to spin up. As ASP.NET does its JIT compiling and things like that. So we do have an increase in our availability metric here once we move to this approach. Okay, so once you get here, which is where many organizations are or were before they started thinking about going to the cloud, you should really think seriously about whether you want to move to the cloud. All right, and so the cloud in this case could be Azure, could be AWS, could be whatever your cloud of choice is. And in some cases, it makes sense to use multiple. Just so you've got some resiliency, because occasionally Azure will go down like for half the country, or Amazon will go down for half the country. I've not yet seen both of them go down at the same time. So there might be some reason why you want to have even multiple cloud vendors. I don't recommend the black hat from XKCD's cloud, though, even though it's underpinning most of the other cloud vendors. Now his cloud works because there's a lot of caching. It turns out caching hides many sins also. So if your database is horribly designed, it doesn't have any indexes, but you have a lot of caching, no one will know except for those poor users that actually have to make that first query. Every other user will just get the cache, and it'll seem like your database is super fast. All right. So now let's talk about a simple cloud architecture that's doing basically the same thing that we have right now with one small change. So we're going to use different icons. In this case, I'm going to use Azure's icons, but it works the same with Amazon. You're going to have a load balancer. You may have app service instances. Those are where your app lives. They aren't actually servers anymore. This is platform as a service where you just upload your DLLs, set up some configuration, and it will host those. You can use an Azure cache or a Redis cache as a shared cache between multiple instances that makes it much easier for you to make updates and make sure that you don't have out-of-sync caches between different instances. They're all going to see the same thing. And then that can sit out in front of your Azure SQL database. And so this is a fairly typical starter point web application that you move to the cloud, where you've got scalability, you've got some caching involved, and you've got your database. Now this works great. This new behavior gives us better scalability. Still haven't done anything about those cache misses for the database, although it's easier to crank up the database performance capabilities once it's in the cloud if you've got the wallet for it. Your cache synchronization is much easier. You don't have any more servers to manage. You do have now monitoring tools that are built into your platform of choice. You've got some learning curve, right? If you're a sysadmin that knows everything about Windows Server and now everything's on Amazon, you're going to need to learn some different tools. But assuming that you're okay with that, you didn't have to write those tools, right? Whereas with the cache management stuff, you're probably writing that stuff yourself with developers, whereas now it's all just built into the platform. And then your uptime, your availability should be much better because you have the ability to have multiple different instances very easily, just like you did in your web farm. And you can manage those quickly and easily, more so than if you had an actual server that you had to deploy to typically. All right, so it's mostly happy faces at this point for comparative purposes to the other approach. All right. So now let's build a bunch of these apps, right? Because your company probably doesn't just have one application. So the next scaling problem isn't so much how are we going to scale the application for users, but how are we going to scale building lots and lots of these apps? Because when you just had one web server and one database, probably what happened is you put a lot of different apps on it. Right? You maybe had IIS and it had a bunch of different virtual routes in it that each represented a different app, or they all went under one, however it was. Your database probably supported more than one app because that's what most companies did. It's still what most companies do. How many of you, show of hands, have like one main database that everything has to talk to in your company? Very many? How many of you are sleeping and not raising your hand? Come on. I know most of you probably are there, right? I've seen that with tons of clients. And if it's true that like only 25% of the people in this room have that now, that is awesome. Because we really want to have more of a system where each application controls its own data, at least if it's complex, right? Or if your enterprise is growing and it wants to be able to continue to evolve quickly. Okay, so when you take this system and you try and scale it in terms of how many apps you're going to build, you end up with something that looks like this, initially, let's say. Right? So you've got a bunch of app service instances for your first app, then some more for your second app, some more for your third app. They're all talking to the same shared resources. Now, one of the reasons why companies like to have shared resources before they go to the cloud is that it's much easier to manage one database server. It's much cheaper to license one database server. It's easier for the DBA to only have to worry about and secure one database server. Once you move to the cloud, the ease of managing one server instance or one database instance or two or three, it's still a little bit more, but it's easier because it's all in one portal. It's all scriptable. And so it's not that much more difficult to spin up multiple databases for different systems. Now that will give you other challenges that we'll look at in just a moment, but from an administration perspective, it's not that much more difficult. And there's no longer the cost of I have to buy another server or I have to buy another database license. Right? Having multiple different databases in Azure or AWS doesn't cost that much more like it did to spend $20,000 to buy a new SQL Server license for a new server. All right, so with this, you run into some new problems, right? So you might have vendor lock-in at this point. These are all Azure web apps that I'm showing with these icons. Substitute in if you're using Amazon. But they are specific to Azure at this point. You've got a shared database in this case still. So that can hurt your availability if you have to do anything that totally takes that database down. It's going to affect all those applications at the same time. Whether that's maintenance or whether that's like somebody accidentally did something, they did an update to a table that they shouldn't have, right? If all the apps require that table, then it's going to take down all those apps. And your shared resources, for example, that data schema, are going to limit your developers' ability to evolve their applications in different ways. So if you have like a common customer table in that database, it won't be unusual for, app A needs these 4 columns, app B needs those same columns but a couple more, so we'll just add a couple nullable columns onto the end of that table. And then app C does the same thing, and eventually you've got a customer table that's got like 60 columns that any one application only needs like 5 or 10 of, right? That's a fairly common sort of anti-pattern that you see at companies that do use one database that every app has to talk to. All right, so we'll address these in a moment, but first there's one other consideration once you have multiple different apps, and that is, how are we going to authenticate and authorize users of this system? Okay, so probably this was already done before now, but we're going to just look and see like what would they have done. The apps would probably require, or at least they would prefer, some kind of a single sign-on solution, so you don't have to have a different login and password and register at every different app in company A. Of course, they have to provide security, so you need to make sure these apps are locked down and protected from unauthorized use. And so they would have done this already. And the simplest thing that would have been done, especially if you're in a Microsoft stack and doing ASP.NET development, is you would have these ASP.NET identity tables, and you would add them to your database. And maybe you did this when you first had application A, and now you just scaled it up to each other app. So each app now is going to have its own login screen, its own forgot passwords screen, and register and all those things, but they're all still talking back to that same database behind the scenes. Now the problem with this approach is that now you've got to worry about authentication in every different app, right? And so if you make an update to how you want to do auth, you've got to go deploy it to every single application. And if you want to try and change how you do auth across the board, that's a big lift at that point to make all those updates. Those tables are also further coupling all those applications to that one shared database. So even if they do decide that they want to kind of go more of a domain-driven approach and start having their application own more of its data, they're still stuck with this tight coupling to that user table in the database that's shared by everybody. So then the next cloud pattern that you'll probably want to look at or embrace is this federated identity pattern. And so federated identity can use any number of different protocols or strategies. But it basically looks something like this, where you have your service that you set up ahead of time down in the bottom right. And so step 1 is to configure your service to trust an identity provider. And that identity provider might be a system that you control, a server that you have inside your network, or it could be an external. It could be a social media identity provider. You could say you can log in with Facebook or GitHub or whatever it might be. Either way, your system is set up with some kind of trust for that other system. And it's going to know that if a token comes in that system vouches for, and it says that this is user so-and-so, that you're going to trust that that's true. So now when a consumer or client comes in to hit your system, you're going to see that they are not authenticated, right? They don't have a cookie, they don't have a token, and so you're going to redirect them to the identity provider. So their first step, even though it says 4 down here, there's really like a step 1.5, where the consumer comes to your service and says, hey, I want your resource. And you say, hey, I don't know who you are. And say, go talk to these guys. And so they run over to the identity provider, and they do whatever they need to do to authenticate, right? They give them their Facebook username and password, and then it comes back and gives them a cookie or a token, and it redirects the user right back to your service. Right? So the user doesn't have to like retype in the URL or anything. They just, boom, they're right back to your home page or your login page, and now you see that they have that token or that cookie, and you let them access the resource. All right, so now you can leverage containers, which is another pattern we're going to talk about here, along with federated identity. You don't have to, but containers is another thing that it starts to make sense to do if you start breaking up those shared resources and make it so that you can deploy things a little more granularly. So we'll talk about federated identity first, and then we'll drill a little bit more into like why containers and what's the point of those. So at the very top here, we've decided that we're going to have our own identity provider. And this is going to be our identity microservice. And why is it a microservice? Because it only does one small thing. It's just worried about identity. And so for your organization, you could deploy this one identity microservice instead of having to implement login features and password features and register features on every different web application that you ever write. So this identity microservice, that's its job. That's all it does. And the client machine is going to authenticate with that microservice first, or it's going to get redirected there if it tried to hit another site first. and then it's going to get that token, and then it's going to present the token to any one of your applications. And so each one of your applications now is running more standalone from the others. It's going to have its own Redis cache. It's going to have its own Azure SQL database, hopefully, that it can have access to. And so they're going to be more independent from one another. So if we have to do updates to one app and it breaks things, it only breaks that app, right? It limits the surface area of things that are getting broken when we break things. But it does introduce other challenges. OK, so the other thing here is that if we are using containers, let's assume we're just using Docker containers in this case. Docker containers are supported by all the different cloud vendors. Docker containers you can run locally on your machine. You can then take that Docker container and you can run it on a build server or on another developer's machine, and it will run exactly the same way on each of those different devices. Then you can take that Docker container, you can deploy it up to the cloud, where again it will run exactly the same way, and it doesn't care which cloud it's on. So that vendor lock-in that you had when you were using a platform as a service, Amazon Lambda or a app service on Azure, where it knows that that's where it's running, that goes away as soon as you start to use containers. And now you could say, based on which one's giving you a better price, which cloud vendor you want to use for hosting your container-based web applications. So there's a number of different advantages you get from moving to containers. That's just one of them in the cloud scenario. All right, so as soon as you move to a scenario, though, where you've got different Azure SQL databases for every different application, the problem that immediately arises is, what do you do about shared data? What do you do about things that happen with application A that application B really needs to know about? Because it's that same customer. They just updated their phone number. All the applications need to know the customer's phone number. How do we get that message out there when these things aren't connected at all anymore? So data sync becomes the next big challenge once you move to this architecture where everything is separate. Everything is like these distinct little applications that live in their own box, but they still need to talk to each other somehow. And so generally, the approach to this that you're going to apply in the cloud is going to be some kind of a message or event bus. And so in Azure, you can use an Azure event bus. You can implement RabbitMQ. You can implement whatever different kind of messaging system you want. There's a bunch of them that you could look at. But the idea here is that when application A gets an update of some sort that is to a resource that other applications care about, like, say, the customer, they can publish an event or a message on that bus that says, hey, customer updated event for customer 123, they changed their phone from this to that, right? And that just goes out over the wire on that message bus. Any other application in the organization, and not necessarily just in Azure, right? You can listen to this message bus from your on-premises machines as well. They can listen to that message bus and look for those messages. And they can just pick and choose the ones they care about, right? So you might have an application that really doesn't care if somebody's phone number changed, and it just lets that message go by. But if it does care about customer updated event, then it's going to get that message and it can update its data accordingly. All right, so this gives you a way to have what's called eventual consistency, where for some period of time, the only app that knows that the customer's phone number was updated is app A, because that's the app they were using when they hit save and they updated their phone number. But eventually, and usually that's measured in milliseconds, all the other applications will receive that event off the message queue and update their own databases accordingly, if they care. Okay? All right, so then let's talk about microservices. Microservices and containers often go hand in hand, and microservices is a big topic. I'm not going to do it justice here today in this talk. You can do a whole talk or whole workshops on it. But microservices basically takes your application, and it's going to take that very coarse-grained app that's the whole thing and make it more fine-grained and easier to scale. All right, so we're going to take this common functionality that maybe is duplicated between apps, or even something that's stable within an app that we don't want to disrupt very often every time we do a deploy. We're going to pull that out into its own separate deployable unit that we're going to call a microservice. Right? It's small and it's independent. It's cohesive, meaning the things that it's doing are related to one another, and we can deploy it separately. So a lot of times when we talk about microservices, the benefit that most people think of is that, yeah, these are great because if this particular microservice is on the hot path for the load of the system, I can independently scale that up, right? Or if this microservice is changing more often than the rest of the system, I can deploy it more frequently. But one of the things that's often overlooked is building microservices for the things that aren't changing at all ever, right? So if you've got parts of your application that are just done and you don't have to change them anymore, those are also good candidates for microservices because you can deploy those things and then just forget about them. And now anytime your app has an update, there's no way you're going to break that other part of the system that is just deployed and done and stable and good to go. And that provides you a lot of peace of mind when you're doing these deployments where you don't have to stress about, oh gosh, did we test everything enough? Do we do regression testing on this part of the system over here? Because it's super critical, but even though we didn't change it, these things might break it, right? If it's a microservice, it's much less likely that you're going to accidentally break it when you deploy something to some other part of your application. Now we saw this already when we pulled out that identity microservice into its own separate container, right? So identity is one of the first things that you can think of that is a cross-cutting concern that every application is going to need that you can easily share. But there are often others, right? So you might have a system where every part of your application needs to get data about your product list, right? So instead of having product list be just a common table in a common database that everybody queries, you can make a product microservice that now is just responsible for listing out products. All right, and that's a common approach that you'll see. Okay, so let's for a moment, let's get concrete about what this application is. And let's say that application A is actually an e-commerce store. And so it has multiple different client apps. There's a mobile app that you can use to shop and buy things on your phone. There's a web app you can go to and buy stuff on your desktop or your phone. In either way, these things are going to talk to this application with the same architecture we've looked at. Now these screenshots are actually screenshots of an actual reference app that you can check out on GitHub. It's called eShop on Web for one that's just a single monolithic app, or eShop on Containers for one that has a microservices architecture, which I'm going to show you some diagrams of here. But all the source code for these is available. These are Microsoft reference apps. Okay. So if we take our app and we split it up into different microservices, we can get an architecture that looks something like this, where maybe I've got for this e-commerce app, and this is what it really is broken out into if you go to the site, maybe we've got a different microservice for the product catalog, a different one for login and identity, a different one for managing your shopping cart, and a different one for managing orders when you check out. All right, so I've only got 3 listed here, but there's actually a couple more. And so now you've got this mobile app that's going to communicate through API calls instead of just loading all the UI like a typical web page does. You've got your web app. It's either an MVC app that just loads everything from the server, or it might be a single page application like an Angular or React app that again is going to use APIs more like that mobile app. They're going to talk to these microservices. They're going to get just the data they need, probably in JSON format, and then they're going to render it on the site. Now, if you use this architecture, which is usually like the first step that you take, one issue you might have is if you have lots of different apps and lots of these different cross-cutting microservices, you're going to end up with this very, very big mesh of connections between all those different endpoints. And it turns out that not every app is going to need every part of the microservices that it knows about. And so securing what microservices should be available to different apps and to different users starts to become a challenge. And if the microservice is the place that knows about that, because right now it has to be, right? There's nothing in between it, then that becomes a challenge for designing your microservices, right? Because now they're not just focused on their domain, they also have to worry about authentication. And not only that, they have to worry about authentication differently based on every different client that might communicate with them, potentially, if that's how your business rules are. But that's not uncommon. And so you have some security concerns there where the client apps might not need everything, microservices have to know too much, and you'd like to limit the surface area of things that are exposed to any given client for security reasons, right? So you're not giving more data than you need to, or you're not offering ways that someone could exploit your system. So the next pattern that you can apply is this API gateway pattern. And the API gateway pattern you can do manually, like this. So you can write your own web API project using ASP.NET or your language of choice, and you can deploy it out there as a separate thing. And then in there, you can put all the rules of how you want to secure things and which apps are registered and which apps aren't and what they have access to, and basically kind of proxy all the data through your API gateway. Alternately, you can use something that's baked into your cloud provider. So if you're using Azure, Azure has this API management feature that you can use as an API gateway that has built in all the things about how you would set up rules for which apps can have access to which backend microservices and things like that. And you can manage that all through a portal instead of having to deploy yet another app to do that. Either way, the benefit is that you're going to have better security over your system. You're only going to expose what you need to expose to each app. All right, so another fairly common scenario that you might have, not necessarily on that eShop example, is accessing secure files. So let's say you've got this issue where users are going to upload or otherwise have access to some kind of large-ish media files, right? They're high-res photos or they're videos. And so the simplest approach is anytime a user uploads one of these things, you throw it up on a CDN, you put it on Amazon S3 or CloudFront or whatever it is, open to the public, but nobody knows the URL, so it's secure. And then you lock down the user's list of all their things, so you have to log in order to see your list of photos or your list of videos. All right, the problem is that once the user gets into that and they've logged in and they see their list, they can right-click on that and find the URL very easily and then post that to Twitter or share it with whoever they want, and now anyone can get to that CDN file. And so to really secure that data, you need to put something in front of it. And so a typical way that you'll do that is you'll have your client machine, and then you'll have your web app, and then you'll have whatever the storage is for that data. It could be a file server, it could be blob storage. And I don't know why all that stuff just flew away, but you'll have this request to the web app, which will then, in turn, make a request, probably HTTP, to that blob service, get the resource it needs, and then send it back. All right, so it's basically shuttling everything back and forth through this web app that you've got. And the reason the web app's involved is because it needs to do that security piece and make sure only authorized users can get to that resource. All right. The problem with this, especially in the cloud, is that usually you're metered on things like bandwidth and possibly on like CPU and usage and things like that. Now, if you're lucky, you've got this blob storage in the same data center in the cloud as your web app, and they have some pricing rule that says if it doesn't leave the data center, we don't charge you. Right? But that isn't always the case, and sometimes because you want to distribute your data across the globe, or you want to have high availability and disaster recovery, so you've got things in different places in the US, these might not be in the same data center, which has performance implications, for one, but also now you might be paying to take this 10 gigabyte video and pull it out of blob storage, send it over to your web app, which is coming ingress into its data center, and then immediately just turn around and stream it right back out to the client, so now you're paying egress again off the web app's data center. So that can be expensive. So you end up with more load on the web app than necessary, because if it's streaming these big files, it's chewing up threads that are holding it for that whole time. Cost is a big concern here, because now you're paying for that data to move multiple times. There's a greater chance of downtime, because if the web app's down, the whole thing falls apart, even though a user might otherwise have been able to get to their resource on that CDN or that blob storage. And so the next pattern here is this Valet Key pattern. And the Valet Key works like this. You've got your user in the top right this time. They're going to make a request to the resource to that web app. Right? That web app, instead of just authenticating the user and then going and streaming the data through it, they're going to return a token to the user and a link to the resource. Right? And so now the user can access that resource with that token. Now that token might be only usable one time, or it might be only usable for a short period of time, like for only 5 minutes or something like that. Typically, it's all going to happen transparently to the user. It's just going to be a redirection that they're not even going to notice. But it's going to allow, when that token is presented to the blob storage or wherever it is that you're hosting that file, it's going to provide access to that user just this one time and be able to stream now directly from the blob storage to the user. So if you're using Azure, there's a feature called Shared Access Signatures that's designed for this purpose. It's pretty easy to set up. And then your file transferring now no longer has to go through your application. It just goes direct, which has all the benefits I just outlined. All right, so then I've got time left here for one bonus anti-pattern in this list of patterns. So I want to talk about this reach-in reporting anti-pattern. Reporting is another one of those cross-cutting concerns that most organizations have some need for. And ideally, it's going to be a separate application. It's going to run a separate space than the apps themselves. And so you might have this approach right here is one of the simplest approaches, is you write your reporting solution in such a way that it just reaches out to the individual databases that each microservice has. And just, it knows their schema, it does whatever selects it needs, and presents the report. Right? This is not great because it introduces coupling. Now, if I want to update my microservice and I decide I need to change the design of something and I rename a table or I move a column around, now that reporting service breaks because it was dependent directly on the schema of my microservice database. It also bypasses the microservice logic, which may or may not matter. Most of the time, that's not a big deal. The bigger problem is the coupling. The reporting service might also negatively impact the performance of the microservices by periodically coming in and hitting their database. So then the next approach addresses the coupling and says, okay, I don't want to know directly about your SQL Server. That's yours. I'm going to let you keep that encapsulation boundary of your microservice that only you control that data and nobody else should access it without going through you. So I'm going to hit specialized endpoints on the microservice that you've set up just for me so I can do my reports. All right, and the problem with this tends to be performance, because now you're making HTTP calls to try and get data, and you probably need a lot of data to build some of these reports, and trying to stream a lot of data over HTTP and trying to do complex queries through an HTTP interface instead of directly against that database is going to be way less efficient, way less performant than just doing it to a database directly. So this gets rid of that dependency, that coupling, but the performance impacts are usually not worth it. So then the third approach is, okay, well, we'll just have a batch job that will have our own reporting database. So we're going to have a data warehouse or some data store, whatever we want to call it, that the reports go against. And this is generally a good idea, right? You want your reporting system to have its own data store that's optimized for its reports. Another cloud pattern that you'll hear is called materialized view. And materialized views are often what you'll use in your reporting database, where they're already set up in the format that queries are expecting, rather than in whatever format the transactions maybe get put into. I didn't have time to cover it in this deck, but you can look for that one. However, this approach, while it gives you some better performance, it still has those same problems with coupling. And so the solution here is to basically stream events to that reporting database. And so anytime a change happens in the microservice that updates its data, it will also create an event that says, hey, such and such was updated, and put that on an event bus or send that to a message queue. And then some data capture service is running that's picking things up off this queue and making updates in real time, or batch, it doesn't really matter at that point, to the reporting server's database. And so this gives you probably good performance. It gives you better real-time reporting than if you just had this batch job that was running like every night at 2 in the morning. And it still gives you that boundary where you're not knowing about the actual schema of the data inside the microservice database. Okay? There's actually a book on this that you can find from this link here at the bottom by Mark Richards on microservices anti-patterns. So he's got a bunch of different anti-patterns in there. This is just one that I wanted to call out, so you might check that out. A couple other things I want to talk about here. Let's wrap this up. We got about 5 minutes left. We might even have some time for questions. First off, when you move to cloud architecture, one of the key things to consider is that you're abstracting away servers and you're moving toward either platform as a service abstractions like functions or apps, or moving toward containers. The cache aside pattern is great for performance improvements if your database is too slow or if it's getting hit by too much stuff. If a lot of this data is just the same thing again and again, it's a good candidate for caching. And caching hides many sins. So if your database is not well optimized, just throw caching at it first before you spend a lot of time trying to optimize it. Containers give you a lot of benefits in terms of deployment and scaling options, and they also eliminate a lot of the vendor lock-in because you can deploy containers anywhere. Microservices, we talked about briefly, they give you much finer-grained control over how your app is functioning, and this translates into better options for how you deploy it and how you scale it, where you can scale each of these microservices independently from one another. You want to have federated identity as soon as you start to have more than 2 or 3 different apps that you need to share a login. It's one of the first candidates for a microservice. You can either implement it yourself using something like Identity Server and just deploy that to a container, or you can use, depending on what your organization supports, you could use ADFS or Azure AD or even social logins with GitHub or Facebook or Twitter or whatever you like. API gateways are useful when it comes to securing multiple different microservices or APIs that you're exposing to your different applications. Valet Key gives you that cheaper, faster way to get large blob files or things like that directly to the client, but still in a secure manner. Then you want to avoid this reach-in reporting where your reporting service knows too much about the internals of your microservices. All right, so that was a lot to cover. I hit on a few different things there. Hopefully some of these were useful to you. I know I started with some basics and tried to move into some things that are a little more advanced. There's about 25 or 30, I think, different design patterns in this book that you can download for free. It's a Microsoft ebook. If any of you have been around doing ASP for a long time, one of the authors is Alex Homer, who used to write a lot of the big rocks, red books on ASP back in the day. So he's still writing books. So definitely check this book out if you want to learn more about this topic. If you need me, I threw most of this stuff up at the beginning, but you can find me on Twitter or emails on here as well. And I think that's all I've got. So are there any questions? Were there any questions on Slack that I should answer? All right, so the question is, what's the best way to share or to determine what is shared with a given API, with a given client through an API gateway based on user role? All right, so the API gateway should know who the user is based on their credentials. And then it can have whatever rules you want, right? Depending on whether you're using your own homegrown solution or if you're using something from your cloud vendor, you can specify the rules that say which microservices it can get to and which specific endpoints it can get to. Now, if you're trying to say which data within an endpoint it can get to, then you're just going to want to pass along that user credential to that API and let that API determine that internally, typically. How do you avoid data sync issues when using an event bus in containers? I'm assuming they're talking about what happens if it's been changed in two places at the same time. Because otherwise, eventually they line up, right? That's the whole eventual consistency. If something got updated in two places and they pass like ships in the night with their update events, that's a more difficult challenge to kind of figure out. That doesn't usually happen all that often in practice, actually, because usually the user's only hitting one thing when they're making an update. But if they do, then that's something you'd have to figure out a way to manage. There's not a cookie cutter silver bullet for that I'm aware of. So yeah, that's a problem you need to solve. Any other questions? Any other questions? Yes, sir. Okay. All right, so there's a question, the short version of the question is, if I have an identity server, I'm using an API gateway, I've got a bunch of microservices, and I add a new microservice, and now I need to determine which users in which scopes can get to that microservice. And currently, it's a pain because I have to go into identity server, I have to add a new scope, I have to set it up to pass the correct scope on to the new microservice. And it's kind of like, for admin purposes, it's like breaking the open-close principle. Because I can't just add new microservices without having to always also go back into the API gateway and mess with things. Is that pretty much true? Okay, so what you could do is you could set up a default rule in your API gateway that says if the user's authenticated, I'm going to have a default scope that just knows like what credentials, what claims they have, what roles they're in, whatever it might be, and I'm going to always pass that same scope data to every microservice, right, and let the microservices figure it out. And you could have a blanket rule that said I'm going to let you get to whatever. Right? I don't necessarily recommend that, but that would be one approach where now you could just add more microservices and it'll just let them in and pass along their stuff. But now you're kind of making it so the microservices have to know, and that kind of defeats the purpose of the API gateway. Otherwise, you've got to do that work on the API gateway. If you can't come up with some like blanket rule, like the one I just described that I don't recommend, that just kind of automatically works for any new gateway, or sorry, any new microservice, you're going to have to implement some kind of custom rule on the gateway that reflects what that service should do or should be allowed to be accessed by. So I don't have a better silver bullet answer for that one either, sorry. All right, so thank you everybody for coming. Hope you enjoy the rest of the conference, and I'll see you later. Thanks.